Okay, hi everybody. So what we're looking at today is two free response questions that I think both of them are pretty dang good questions. So one of them is like the QQT, the qualitative quantitative translation question, and one is a paragraph length response question, which is the two types of questions that we'll see on the AP test. So I think these are good questions. I think they're good practice. And yeah, let's dive right in. So with the first one, we're saying a block is initially at rest on top of an inclined ramp that makes an angle theta naught with the horizontal. The base of the ramp has a length of d. So we got d right here. After the block is released from rest, it slides down the ramp onto a rough surface until it comes to rest at a position x equals 4d from the base of the ramp as shown in the figure. So it stops right there. There is negligible friction between the block and the inclined ramp, while the coefficient of kinetic friction between the block and the rough horizontal surface is mu sub b. So we have friction here, but we don't have friction on the ramp, so frictionless. All right, cool. So the first part, what we want to do is we're going to sketch this graph on our own piece of paper, but I have the surface I can do right here. So what we're doing is sketching and labeling the following quantities given to us, and as a function of position between negative d and 4d. Calculations for values aren't necessary, but we want to use the same scale. Okay, cool. So pretty much what we're being asked is we want to graph the kinetic energy throughout distance and the potential energy throughout distance. So what I want to start with is I'm going to start with this potential energy, because what I know is during this first part, if I think about the energy in my system, if I draw one of these LOL diagrams, I can say, okay, at the very beginning, if I'm looking at the system of the block and the Earth, at the very beginning, the type of energy I have is just going to be potential energy, because my block is at some height, and it says that my block is at rest. And then I'm going from all that potential to kinetic energy. So from there to there, all of my potential goes to kinetic. And then after that, I kind of keep this LOL diagram going, I have this kinetic energy that then, let's see, if I'm tracking out, let's say the block and the Earth is still my system. Let's see, it goes from kinetic energy to, at the end, it's stopped and it's not at any height. So it looks like I go from having this kinetic energy to nothing. So it looks like I have work. So I'm going from UG equals my kinetic energy, which then equals the work done by the frictional force throughout this 4D slide. So the first part, what I want to do is I want to set up this idea from, this is happening from negative d to 0, this exchange. And then this exchange, kinetic to work, is happening from 0 to 4d. So what I want to think about, I think it's easier to think about how our potential energy is changing with this d. Just because potential energy, the equation for it is a little bit more straightforward. When we're sliding down, we don't really know how the velocity is changing, so it's going to be a little bit easier to analyze what's happening with the change in height. We know that our equation for UG is just going to be mg times the height, or the change in height, which is a lot easier to think about in terms of this dimension d, as opposed to the kinetic, which is 1/2 mv squared. It's hard to think about how this velocity changes with distance d. So let's go for it. Let's try it out. So I'm going to kind of redraw this triangle down here. And I know that throughout this distance d, I have this angle of theta naught, my block is changing some height. I'm going to call it y naught. So my block is undergoing this height change from y naught to a height of 0. And I want to think about how is that related to d? How does this height change relate to the distance that it travels d? And so what I can do is I can say, well, this looks like I have a triangle. I have something going on here that's a trig problem pretty much. I have this y naught, which is what I want to know. I want to know how is y naught related to d? So what I can set up is, well, I have this angle, I have the piece of the triangle that's opposite of that angle, and then I have the piece of that triangle that's adjacent to that angle. So I can really set up tan of theta naught is equal to y naught over d. And if I want to get y in terms of d, I can just multiply d to both sides and say y naught is equal to d tangent of theta naught. And if I think about it, tangent of theta naught, like right now I don't have an angle, but I know that this angle is constant, and the tangent of a number is just a number. It's not something that changes. So this y naught is changing directly with d. If we think about kind of like y equals mx plus b form, we have y is changing based on, really tan theta is just going to be the slope times d. So y is directly related to d. So we have this direct change. We have this direct relationship. If I kind of take it a step further, I can say, well, UG, this gravitational potential energy, equals mg times y naught. That's kind of my initial, or my change in y. I can plug that in here. I can say, well, UG is equal to mg tangent theta naught times d. So this potential energy is directly related to d. We see that we have this direct relationship, this linear relationship. They're linear related to each other, linear relationship. So it's not like we have, it's related to d squared or square root of d or anything like that. It's our potential energy is directly related to d. So let's set that up. Let's draw that out. We know that at the very top, we start with all of our gravitational potential energy. So I'm going to put it up here. Say, hey, we start out at this maximum. And then by the end, when we reach this position 0, that's where we said all of our energy turned into kinetic energy. So that's where we have 0 potential energy. Come in here and sketch that out. And I'll label this as UG. And then if I'm looking at this, well, what I know about energy is that energy has to be conserved. Throughout this whole entire motion, the amount of energy that we have is conserved. It's changing from potential energy to kinetic, but the total has to stay the same. So I know that at this location, that's my maximum position of kinetic energy. I know that this total energy, this UG, is now my kinetic energy. And I have to make sure that this is conserved throughout that motion. So really, it's just going to look like the inverse of our potential energy graph, because we have to keep it constant. So let's draw that in and then kind of look at that and analyze that. But so if we look at this, at every single location here, we see that our total energy is going to add up, or our potential energy and kinetic energy will add up to our total energy, which tells us we're conserved. Here we have about half kinetic, half potential. So our total, if we add it up, is just equal to our total initial energy. We have this conservation of energy. Here we have 1, 2 for our gravitational potential energy. We have 1, 2, 3, 4, 5, 6, 7, 8 of our, this may not have been the best example, that's okay. But we see that throughout this, energy is conserved. This shows us conservation of energy. This shows us that the total is always constant. All right, now we're looking at this part, the kinetic energy part. We said that during this motion, our kinetic energy is turning into work. So it's leaving our system. So we're going to have now, we don't have the total is not going to be constant anymore. The total energy is leaving our system via this work. So what we can say is we know that work is equal to our change in energy, and it's also equal to our force times our displacement. We know that in this case, the force that is causing the work is the frictional force. So we can replace that. We can say it's our frictional force times our displacement is equal to our work. So we can say then that our frictional force is just equal to our coefficient of friction times our normal force, and then we have times this displacement. This is our equation for our work. And what we see here is that this is directly related to our displacement, directly related to D. Again, we have this linear change. And then we can also say kinetic energy is equal to our work, right? We said we change our energy, all of this kinetic is turned into work. So we can say that our kinetic energy at the beginning equals our work at the end, and our work is just equal to this UBmg times d. So it's directly related to d, this displacement. Again, we have this linear relationship because it's directly related to d. So what we can say is, let's draw this in here. We see that we have, again, another linear relationship. We have a situation where at 4D, we have 0 energy in our system. All of our energy is left. Our block isn't moving. It's all left due to this work by friction. So we have, there we go, and that is our graph. Cool. So we got our sketches. All right, here we say the block is released from the top of a new ramp that has a base length of 2D, but still makes an angle theta naught with the horizontal. A student is asked to predict whether the final horizontal position of the block will be twice as far from the base of the ramp compared to when it was released from the original ramp. The student reasons that since the block will be released from a new height that is twice as high as the original height, the block, that's the same sentence. The block will have more energy when it reaches the base of the ramp. So it will slide farther along the right surface before stopping at a position x equals 8d. So yeah, what we're looking at here is this situation where they ask us what part of the student's reasoning is correct. So when they ask us that, all we have to do is restate what the student said. So if we're ever asked this to talk about what is correct or what isn't correct, what we want to do is kind of what I did here, is go in here and then kind of split up every statement that the student's saying. So it can be the most basic thing or it can be really complicated, but we want to break it into the most basic things that the student's saying, the most basic ideas. So here we have this purple idea. The student reasons, or pink maybe, that since the block will be released from a new height that is twice as high as the original height, so that's a statement. The new height, maybe I'll get rid of some of it. So the new height is twice as high as the original height. That's a statement. That's part of the student's reasoning. So we can check that, see if that's right, see if that trick works out. The block will have more energy when it reaches the base of the ramp. That's another statement. That is something that we can argue whether it's true or false. It will slide further along the right surface before stopping. So that's another statement. And then this last part, at a position x equals 8d. So that's another statement. So one thing I want to just kind of point out, these are two different statements. It could slide further without sliding 8d. If it goes anything greater than 4d, then it has slid a greater distance. So this statement of position x equals 8d, that's separate from it sliding further. So that's just a little thing to point out. So what aspects are correct? This is tricky. This is not going to be something that we can just kind of be like, yeah, that's right. We have to kind of think about this. We have to think about what's going on and analyze our situation. So yeah, let's kind of get in here and analyze it. Let's think about what we got going on. Let's get rid of this. All right, so let's do it. Let's break down these situations. The new height is twice as high as the original height. All right, so that took me a second to kind of figure out. I'm a little bit rusty with my trig. But yeah, let's think about that. So first we have this situation where the ramp had a base of d, and we had this idea that we said tan theta naught is equal to this y naught over d. So let's think about it for a bigger triangle, one where we have a base of 2d, the same angle, and some y. So if we set this tangent up again, we can say tangent of theta naught is equal to this new y over 2d. And if we look at this, well, tangent of theta naught has to equal tangent of theta naught. These tangents have to equal each other. This is the same value. So we say y naught over d has to equal y over 2d. So it looks like if we kind of solve this out, we can cancel out one of those. It's like y is equal to y naught. So it looks like that is a correct statement. The ramp is twice as high. So instead of rewriting it, what you would do is you would rewrite it. I don't want to rewrite it, so I'm going to say that this pink phrase is correct. So that is a correct reasoning. The black will have more energy when it reaches the base of the ramp. Well, yeah, that one's going to be true, right? We can say, well, if we increase our height, oh, that was a good voice crack. If we increase our height, then we increase our, if we increase the height increases. That height is directly related to our gravitational potential energy. We have this equation that says mgy is equal to our gravitational potential energy. So if we increase the height, we are going to have more energy at the beginning, which means we'll have more energy at the base. The same exact LOL diagram, the same thing holds. So if this goes up, then we'll have more kinetic energy because we're putting more energy into our system. So that one's good. So we'll slide further along the surface before stopping. All right, let's look at that. So what we're saying is, again, this LOL diagram, everything that we did up here still holds. All right, we wrote it in very general terms. So what we can look at is we said, well, this potential energy equals the kinetic energy, which equals the work. So let's kind of skip a step there. Let's not even look at the potential or the kinetic energy. So we said that this UG is equal to our work. What we're saying is we doubled our height. So this is kind of our situation 1. In our first situation, we had this mg y naught is equal to force of friction times d. We said in this first case we had mg times whatever let's call it y naught is equal to ub mg times 4d. Right, that was the distance that it slid before. Now in this new situation, we're doubling the height. So we really have double this potential energy. We can say mg times 2y naught is going to equal our force of friction, mg, times some sort of displacement, some new displacement. I'll call it lowercase d because we want to solve for it. So what we can say is, well, before we had mg y naught is equal to mu b mg times 4d. Actually, let's cancel some stuff. Boom, boom. Just to make it easier. So we say 2y naught is equal to ub times some d that we want to solve for, some displacement. Here we can say y naught is equal to ub times 4d. So let's do some substitutions. We can say y naught is equal to this, so we can sub that in. 2 times ub, or mu b, sorry, 4d is equal to mu b times d. Cancel that out. Oh, we have 8d is equal to our lowercase d, this displacement. So it does look like because we doubled, or well, that kind of was two birds with one stone. We proved there that if it has more energy because it's related to force times displacement, we have more, it will slide further, and then we also just kind of came in here and proved that it will go a further, it will go to 8d. Cool, so that is all of the student's reasoning. Which aspects are incorrect? Well, we just saw that the student had correct reasoning overall, so that's going to be a big old none. The student is completely correct, which is kind of cool. I don't know if that's usually the case, I don't know if that usually happens, but hey, it's cool if it works out. Derive an equation for the new final position of the block. Express your answer in terms of d. So this is kind of what we just did, but let's come in here and do it a little bit more officially. So let's set up two situations. This before, or maybe we'll just call it d, and then we'll call the other one 2d. This is the situation where the ramp was a length of d. This is for when we have a length of 2d. So here we can say, well, we started with the situation that the UG is equal to the kinetic energy is equal to the work. And yeah, let's just focus on one at a time. We said here that the potential energy is mg times delta y is equal to our work, which is the force of friction times the displacement. We said here that the y, if we look back at our trig, theta naught, this is d, because it's y naught. We said that y naught is going to equal tangent of theta naught times d. That was from our trig earlier. And say before we had mg times, I'll put the d there, d tangent of theta naught is equal to, I'll just call this equal to the energy in our system is equal to mu b mg times, we know the displacement is 4d. Alright, so that's kind of a, I guess we can do some canceling, but we can say d tangent of theta naught is equal to mu b times d, so we can cancel that too. Tangent of theta naught is equal to mu b. Okay, cool, whatever. So we did some canceling, that'll help us out in a second. So now we can say, let's start with the same exact situation. Our total energy is equal to our potential energy, which then is transferred to kinetic, which is then transferred to work. We have the same setup where we have mg times delta y equals force of friction times d. The only difference here is that we've said that our height was equal to 2d tangent of theta naught, which is then transferred to our work, this mu b times the normal force times some new displacement d. And then again, we can cancel some stuff out, boom, boom, and say 2d tangent of theta naught is equal to mu b times this displacement that we don't know. And then we can do that substitution that we just talked about. We said mu b is equal to tangent of theta naught, so let's sub that in. 2d mu b is equal to mu b times this displacement d. And then we have, this is kind of a little bit sketchy, 2d is equal to this displacement. What happened? So we definitely have the doubling piece. Let me pause this really quick and think about what happened. Okay, so I see what happened. I forgot to bring this 4 down. So we had this mu b mg times 4d was our original displacement. I forgot to bring the 4 down. So we have mu b times 4d. So we have this tangent of theta naught is equal to 4 times mu b. So then we can do that same substitution like we just said we were going to do. 2d tangent of theta naught is equal to 4 mu b is equal to mu b times some displacement that we're solving for. Cancel that out. 8d is equal to our displacement. There we go. That worked out a little bit better. Alright, and then this final one in the following question refer to the relationships written in part C, not just the final answer obtained by manipulating those relationships. So we don't want to just be like, oh yeah, the answer was AD, so we're good. For any correct aspects of the student's reasoning identified in part BI, how is the student's reasoning expressed by your mathematical relationship in part C? For any incorrect, we didn't have any incorrect stuff. Alright, so we just have to say, okay, we said 4 statements, and we just have to identify which parts match up with the student's statement. So the new height is twice as high as the original height. So that was kind of this tangent idea. I guess theoretically we should have written this piece down here, this doubling height, but this would have been a step in our equations, and we could have said that this highlights this idea that the height is going to be doubled. So that is highlighting that idea. This idea that tangent of theta has to be constant, tangent of theta naught. The next statement is the block will have more energy when it reaches the base of the ramp. So we said that we have this idea that this potential energy is equal to the total energy in our system. So here we have this energy is equal to our initial energy, this mgd tangent of theta naught. And here we have this doubled piece. So we see that our total energy in our system is doubled. So we can reference, that aspect of, gosh dang it. we can reference that part of our equation. This idea where we said, oh, we double our potential energy because we double the height, so we see that the total energy increases. So we'll slide further and stop at 8D. So this one is going to kind of be, we'll sync that up because we see the distance is just going to be this 8D. So we can really just reference this final piece where we say, oh, okay, well, we doubled this, so the distance is going to double. Yeah, so that is a qualitative quantitative response where we're looking at the equations and we're using the equations and then we're kind of making sense of them and using them to support an argument.